Okay, so in the previous group theory video, we were unable to complete the solution to this exercise. So let us first do that. Let's recall that in this exercise we are given a group G of order 9, which is generated by two elements A and B, such that A cube and B cube are equal to identity. Here again Herstein has used presentation of groups, which we don't know. However, we will see later on that this group turns out to be a specific group. Here our group G is actually J3 cross J3. C section 30. Now let me tell you, I think I have already said something about this thing, but anyway, let us just again go back to that thing and at least see what this means. If we are given two groups H and K, we are not saying that H and K are subgroups of some group or anything like that, just some two groups H and K are given to us. Then we can consider the Cartesian product H cross K of the sets. Now we want to turn this set into a group, and this can be done in a very natural way, like this. If we consider two elements in this Cartesian product, so they will naturally be ordered pairs, where the first coordinate comes from H and the second one comes from K. So if we take two such elements here, we define their product in a very natural way like this, where the product H1 H2 is calculated in the group H and the product K1 K2 is calculated in K. And it makes sense also because H1 and H2 are elements of H, so the operation we have in this product in between H1 and H2, that is the binary operation of H, and here we have used the binary operation of K. And one can show that this product turns H cross K into a group in a very straightforward manner, and this is one such group. In the more conventional notation, I mean J3, we are using J to represent the set of integers in this book, and J3 is the group of integers modulo 3 under the operation addition modulo 3. In the more conventional notation, this same thing is Z3 or Z3. So that means our G is actually this. And here the binary operation of course is this, where the component operations are, both of them are of course addition modulo 3. Now why this type of description forces G to be this group only, that we will see in section 213. Okay, for now we just assume that that is the case, this is how things will be. And now we want to, now that we know actually what the group is, we want to calculate its automorphisms. We want to find all of its automorphisms. So we will now first of all take an automorphism, any automorphism of this group, and see how it behaves. Then we will, depending on that, we will try to search for functions satisfying those properties that we will find out from that taken automorphism, and see how many of those functions or what of those functions ultimately become automorphisms. Okay, so that is the strategy. But before we do that, we would like to simplify the notation here. For simplicity, we denote the element alpha comma beta belonging to this by C alpha beta. If you are finding this somewhat confusing, recall that in this book, this alpha enclosed within square brackets has a meaning. It's a notation denoting something specific. This component as well as this second component, they are all coming from J3, right? And J3 is the group of integers modulo 3 under addition modulo 3. Now, according to the notation used in this book, this means the congruence class modulo 3 containing the integer alpha. Alpha is an ordinary integer. So, in J3 we have these three things. This is the congruence class modulo 3 containing 0, this is the one containing 1, and this is the one containing 2. And what they really are is this. This consists of all the integers that are multiples of 3. This consists of all the integers that leave the remainder 1 when you divide them by 3. And here we have the integers that leave the remainder 2 when we divide them by 3. So that's what they are. So if we keep all the notations intact, then the general element of this group should look like this. However, we cannot expect to, it cannot be expected that we should write this again and again. If we do, that's just a stupidity. So that's why we have simplified the notation, and in place of this we are going to write this. They mean the same thing. Okay, now let T be any automorphism of G. Then for any, in the simplified notation, any C alpha beta belonging to G, we have, now this is something which can be easily verified. Zero 1 T to the power beta. Now you may think, how can one easily verify this? You see, of course, alpha and beta are ordinary integers, so there are infinitely many choices for alpha and beta, but only finitely many of them ultimately matter. You see, if you take alpha equal to 0, again there is no point in considering alpha equal to 3, because all multiples of 3 are the same. These two alpha, say alpha and alpha prime, they give you the same congruence class. So it's enough to consider only 3 values of alpha, 0, 1 and 2. Just like that, only 3 values of beta need to be considered to take into account all the possibilities. So there are only 9 possibilities. You can directly verify in each of those possibilities that this equation will be true. And keep in mind that here T is any automorphism, but it does not matter. The fact that T is an automorphism will allow you to see that this is true in all those cases. So that's how one can verify that this is true. So now note that whatever T is, ultimately T is being determined by these two images only, the images of C10 and C01 under T. Once you know about them, or once you know what they are, you know the entire T. So T depends on only C10T and C01T. Okay, now what else is true? In verifying this formula or this identity, we only need the fact that T is a homomorphism. But now additionally, because T is an automorphism, T is one-to-one also. Since T is one-to-one or injective, and C00T is equal to C00, we must have C10T and C01T both belonging to, of course, the group G, but none of them is the identity. Okay, what have we written here? C00 clearly is the, I mean, if you really go to the verification that this J3 cross J3 is a group under that component wise defined binary operation, there you will see that the identity in this group is just the identity in this group, first group, comma the identity in the second group. That ordered pair is the identity. So C00 is the identity here. Now because T is a homomorphism, it will map the identity onto the identity. Now since T is injective also, and C00 and C10 are two different elements in the group, so these two things will also be different. Injectivity or one-to-oneness of T implies that different inputs will give you different outputs. Like that, this also cannot be the identity. So that's why whatever these two images are, they are not the identity. Okay, so we have finally come to this to know these things about T. If you take an automorphism, then these should necessarily be true, that such an automorphism T should behave like this. And additionally, what about these elements? There will be some elements in G, but they will not be identity. Now if we go in the opposite direction, if we start from these things, can we get an automorphism? Okay. Now one can easily verify that for any function S from G into G such that C alpha beta S is equal to C10S to the power alpha 1S to the power beta for all C alpha beta belonging to G, and such that this and C10S and C01S belonging to this. If you have a function S from G into itself which satisfies these conditions that we have got here, which are necessary for an automorphism, if you take those, if you start with those conditions, if you have a function S that satisfies those conditions, then one can verify that S is a homomorphism. And in this verification, of course you will use this identity, but one more thing that you will need to use is the fact that this group is an abelian group. So these things that we have written here, they commute with each other. Okay, so you can change the order in whatever way you want. So using those things, it's pretty easy to show that this is, we cannot at once say that S is an automorphism, because this and this are necessary conditions for T to be an automorphism. We don't know whether they are sufficient or not, but anyway we have started from those conditions, and we see that at least S is a homomorphism. Okay, now when will S be an automorphism? Okay, now for S to be an automorphism, now what else do we need? We need S to be one-to-one and onto. However, note that S is a function from G into itself, and G is a finite set. So we know from a previous exercise that S is one-to-one if and only if it's onto. So to show that S is an automorphism, now it's enough to show that S is either you show that S is one-to-one, then it's automatically onto, or you show that S is onto, then it's automatically one-to-one. So you just need to show one of those two things, the other will automatically follow. So that's why we write like this: since S is bijective, should be, yes, since S is bijective if and only if it is injective we now look for conditions so that S is injective. Okay, so now it's enough to show that S is, I should not have said show that, but we want to know when S is injective. So if we find that S is injective for these extra conditions, maybe something else, then that extra condition along with these other things will tell us that S is injective and S is a homomorphism that we already have here. So automatically S will also be surjective and hence bijective. So then it will be an automorphism. Okay, so now for injectivity, what is actually the condition for injectivity for any homomorphism? Note that already we have S as a homomorphism. So it is injective if and only if its kernel consists of only the identity element. So let C alpha beta be any element in G such that the S image of C alpha beta is the identity element. That means we have considered C alpha beta in the kernel of S. We now want to see what conditions are imposed on the element C alpha beta, or more specifically on the integers alpha and beta. So this is equal to C 0 0. Now this will be equal to this. So from this equation we have this condition: C10s to the power alpha is equal to C01s to the power minus beta. This implies S is injective if and only if the cyclic subgroups this cyclic subgroup and this cyclic subgroup, that is cyclic subgroups in G generated by C10s and C01s, if and only if the cyclic subgroups satisfy this condition that they should intersect trivially. If they are intersecting trivial. Okay. Now from this equation, how one is getting this equivalent condition, that is, if this is true then this is true, and conversely if this is true then this is true, that I leave to you. Okay, you try to figure out how one obtains this from this, or what is how do we justify this last line. This implies that S is injective if and only if the cyclic subgroups intersect trivially. Just think about it. Okay, it's not that difficult. So that means apart from having S like this, apart from these two conditions, we should have this also. So this further narrows down our search for these images. We now know something more about how to choose C10s and C01s. Whatever they are, the cyclic subgroups they generate should intersect trivially, and from this we will now be able to see what the automorphisms are. All the non-trivial cyclic subgroups of G are, because G has only 9 elements, so it's rather easy to find all the cyclic subgroups. One of them is generated by C01, and that turns out to be the same as the one generated by C02, and they have these elements. C00, this is the identity, C01 and C02. Another cyclic subgroup is the one generated by C10, which also turns out to be equal to the one generated by C20, and its elements are these. If you look rather closely, both these cyclic subgroups are actually isomorphic to J3 or C3. Go back to all the things where and see what this C alpha beta really means, then you will know what I mean. Okay, so these two cyclic subgroups are there, and apart from them we also have these. The one generated by C11, and this turns out to have these elements C00, C11 and C22, and there is one more, the one generated by C12, and that is the same as the one generated by C21, and its elements are these. These are all the cyclic subgroups that G has. So that means now we can see how many different ways we can have this. Okay, this means that if we have C01T belonging to C01, there is no reason for matching this 01 with this 01. Okay, this according to whatever we have done here, this image will be a group element that is something other than the identity C00. So here this is one way of choosing things. If it happens that this image belongs to C01, then the other one will not belong to this. The other one will come from the other cyclic groups. Then C102 will belong to, so 01 is gone, we have 10 union 11 union 12, and of course the identity element has to be removed. Note that we already know that C01T is not equal to C00. Okay, so I am not mentioning that here. Here also, if we want, there is no need to mention this minus C00, but just for the so that we don't forget that none of these can be the identity, so we have written this. Okay, and the fact is that any such choice okay, but before writing anything more, let us see what we have here. If you choose C01T from here, that means if your C01T is either C01 or C02, but not of course C00, then the cyclic subgroup generated by C01T, that means we were talking about S, now suddenly I have taken T. sorry, S, and this is also S. So if our C01S is C01, then the cyclic subgroup it generates is nothing but this itself, this cyclic subgroup. And the same is the case if C01S is C02. Any two of those possibilities gives us this cyclic subgroup itself. That means in this place you have C01, the cyclic subgroup generated by C01. And if you at the same time if you choose C10S from the rest of the cyclic groups, that is if your C01S is either C10 or C20 or C11, C122 or C12 or C21, then the cyclic subgroup generated by this element will either be this or this or this. Whatever the case may be, this intersection will be trivial. Okay, in spite of all those possibilities, this intersection will be trivial. And any such choice, and that's why, because this intersection will be trivial, the corresponding S and that corresponding function will be an injective homomorphism and hence automatically an automorphism. And from our analysis that we did there, we know that any automorphism must satisfy these things. So now the question has now come down to this: in how many ways these choices can be made? Each such choice will give us an automorphism. That's what let us first write that any such choice gives rise to an automorphism. Actually, this itself determines everything, all the automorphisms. You now know how to choose those two images, C01S and C10S. Once you make one such choice, you get an automorphism correspondingly. You make another choice, you get another automorphism. So like that you will get all the automorphisms. So the solution ends here, but let us also see how many we will get. The other automorphisms can be similarly obtained by other possible choices for C01S and C10S. See, here itself there are many choices, but of course besides this there are other ways of choosing C01 and C10 also. Instead of choosing C01S here, from here, you can decide to choose it from here. Then your C10S should be either in C01, this cyclic group, or this cyclic group, or this cyclic group. Okay, so many such possibilities are there. All of them will give us an automorphism. And that's why in total we thus have, now once we see how we are choosing the things, the number comes out. how many choices are there for C01S here in this way? 2. Okay, so that means C01S can be chosen in 2 ways. For that, corresponding to that, C10S can be chosen in how many ways? 1, 2, 3, 4, 5, 6. Okay, so C01S and C10S together, they can be chosen in 2 times 6 ways. But C01S, instead of choosing it from here, there are for that itself there are 4 choices, right? This is one choice, this is the other choice, because there are 4 cyclic subgroups. So that's why the total number is 4 times 2 times 6 equal to 48. Different automorphisms. Of G, that is the automorphism group of G, of our G will have 48 elements. It will have order 48. So here the solution ends. Let us now go to the next section, that is Cayley's theorem. Okay, Cayley's theorem is a result that tells us that no matter what group we have, suppose we have a group, we can always realize that group as a somewhat more familiar group. We can reduce the abstractness. For example, here this is an extremely abstract group. The way this group in this exercise, the way the group has been given, it's an abstract group because the exercise says that it is generated by 2 elements A and B, and it has order 9, and A cube and B cube are equal to identity, where A and B are just some symbols. We don't know anything else about them, or the only thing is that we are given how they behave with one another and with the other things, how they generate the group, that only that much is given to us. As objects, A and B are just some abstract entities, some abstract symbols. Now sometimes it becomes extremely difficult to work with abstract groups. It's much more convenient to work with some familiar objects, not some abstract symbols. So what one can try to do is this. Say this is your abstract group G, where there are some symbols. You know all the symbols in G, you know the binary operation in G, but still the system is unfamiliar to you because it is abstract. You don't know what the symbols individually, if even they mean anything other than the fact that they are some symbols. So what you do is you try to find another group, say G prime, about which you know the elements in this are not just some symbols, but they are some things with which we are more familiar. For example, you may have in G prime some functions, or you may have in G prime some matrices. Now definitely matrices are something with which we are more familiar than just some peculiar symbols. Or for example, this G prime can have some sort of some other entity, some tensors, anything else, some vectors, anything but not just some abstract symbols. So now the strategy is this: can you identify G inside G prime? And the meaning of that is this. Specifically, the question is this: can you find a subgroup H of G prime that is isomorphic to G, so that if you are able to do that, then there is no need to work with the abstract group G. You can then work with the concrete subgroup H of G prime, because the isomorphism tells you that there is no real distinction between G and H group theoretically. That is the question. So that means if we are given a group G, now the real question is this: does there exist a familiar group G prime so that you can find something inside G prime, a subsystem which is identical to G in group theoretic respects? And the answer is yes. And the result that says that yes, this is always possible, that is Cayley's theorem. In the beginning days of group theory, people did not work with abstract groups. In fact, the idea of abstract groups was given much later. Most of the groups arose in the form of something concrete. In most of the situations, groups arose as sets of functions or transformations of some geometric object. For example, one may ask, what is the group of all symmetries of a rectangle or a quadrilateral like this? In what are the transformations that you can apply on such a geometric figure so that after doing the transformation the figure looks the same? If you find such a transformation, that is called a symmetry of that figure. So those symmetries form a group. So groups arose in such ways, okay, some concrete set of transformations, or maybe some as a group of matrices, something like that. The English mathematician Kaylee understood that any group can always be, or because we have said these things now, Kaylee understood that this G prime can always be taken as A of S, where A of S is, you recall, A of S is the group of all bijective mappings on S, that is one-to-one onto mappings from S to itself under the composition of mappings, that group, the permutation groups. So if you are given a G, then there always exists some non-empty set S such that you can identify G inside this group of permutations. So let us now state the theorem and prove it. But let me also read what the author has said in the beginning of this section. When groups, which is actually whatever I said, it's from here only. When groups first arose in mathematics, they usually came from some specific source and in some very concrete form, like transformations or matrix groups like that. Very often it was in the form of a set of transformations of some particular mathematical object. In fact, most finite groups appeared as groups of permutations, that is, subgroups of Sn, the symmetric group of degree n, which is actually nothing but your A of S only, where now S is a finite set having n elements. The English mathematician Kaylee first noted that every group could be realized as a subgroup of A of S for some S, and so that's the thing. Okay, so this is Theorem 291, and this is due to Cayley. And the statement precisely is this: every group is isomorphic to a subgroup of A of S for some appropriate set S. Let us now prove this. Let G be a group so now the first job is to decide what S is. Now for S in this proof we take the set G itself. Okay, so that means we will be considering A of G for the set S. We use the elements of G itself, that is, we take sometimes I forget to things are left as L that don't become T. We take S equal to G. Okay, so now let us take S equal to G here. So that means this is our G prime. So here we have G. A figure is always helpful, no matter how trivial. Now we need to devise a way of identifying G inside A of G. In other words, the statement says that this is isomorphic to a subgroup of G. What is that isomorphism? Or if you take an element G, how would that element look like inside A of G? Or more specifically, under that isomorphism, whatever it ultimately turns out to be, what is the image of G? And that image of G you can clearly see, since it has to be in A of G, it should be a bijection on G, that is, it should be a one-to-one onto mapping from G to itself. Some sort of mapping tau. The fact that it depends on G is denoted by putting G as a suffix. Okay, we now want to know what tau G is, or what sort of tau G we can take for any G belonging to G. Define, we are now going to define a map tau G from S, which for us is nothing but G into S, by this formula. x tau g, that is the image of x under tau g, is defined to be equal to xg. Note that because your input is coming from G and this G is also a group element, the output xg is nothing but the product of the group elements x and G in our original group. Okay, so that's how we have defined the function tau g in, so far tau g is only a function from G to G. Note that before we draw something like this or claim that tau g belongs to this group, we need to show that this tau g actually is a one-to-one and onto function. It's a function from G to G, fine, but now we need to show its bijective. And there is no problem with its well-definedness. You take any x in G, that gives you an output again in G, and this output is unique. For a given x, there is a unique xg. Clearly, this is well defined. Okay. For any y belonging to, we have started writing G itself now. Let us maintain S. For any y belonging to S, there exists yg inverse belonging to S. These things now make sense because S is nothing but the group, such that let us keep this figure. Such that what is the tau g image of yg inverse? By definition, it's this, which becomes y. So that means any element in S, where treat this S as the second set in this map, there is an inverse image of that element under tau g, so that the image of that inverse image under tau g is this y. So that means our tau g is an onto mapping this is onto or surjective, same meaning. Now next we try to show that tau g is injective or one-to-one. Now let x and y be two elements in S, but now treat S as the domain, such that their images under tau g are equal, that is outputs are equal. We can now show that the inputs x and y are also equal, then it will be one-to-one. Then this is xg and this is yg. From which we get by the right cancellation law this equation x equal to y, because whatever we are doing is happening after all in this group. These elements, at least they are in this group, so this equation is in this group, so you can cancel g from both sides. Doing that, you get x equal to y. So tau g is injectable, so it's 1 to 1. So that means it's a bijection. So now we are justified to say that tau g belongs to A of g. Thus, this belongs to A of g, or the same thing, A of s. Okay. Now if we define our function psi using this association, what do we get then? Next, define a function psi from g into A of s by this formula. The image of g under psi is this mapping tau g. Okay, so for now for an element g in the group, we are getting the image in A of s or A of g, same thing, and that is tau g, tau suffix g. And this map is also well defined. For any input in g, the output tau g first of all is in this set, and for a given input g, it is unique. Clearly, these cases may look like it's always going to be like this. You can just simply write clearly this map is well defined, but sometimes that is not so clear and obvious. Okay, in these cases it's obvious. Clearly, psi is well defined. One such case will come shortly. Okay. Now we want to now first show that this psi, the mapping we have defined just now, this is actually a homomorphism. Never lose track of what you are doing. Okay, we wanted to show that tau g is it's a map, psi is also a map. We wanted to show that tau g as a mapping is 1 to 1 and onto. That's all. Okay, although tau g is actually a map from g to g, but there is no need to show that tau g is a homomorphism. That's not what we are after. Here, however, because we are searching for an isomorphism, we now need to know whether this psi is a homomorphism. Here our main concern is in showing that psi is a homomorphism, and that too a 1 to 1 homomorphism. Tau g has nothing to do with homomorphism. Okay, so what are the ingredients that we will need to pull this off? We need to show that psi is a homomorphism. So we will need two elements here from G, and then we need to show the things we need to show. Okay. But because the end results are themselves functions, so we need a third element also. Let G, H and X be three elements in G. Note that okay, now look at these calculations. X, tau, G, H. G and H are two group elements, so GH is their product, that is also a group element. So this tau GH is the corresponding function, tau function. it makes sense, and you can apply that function on x, because x is coming from G, that means x is coming from S is nothing but G. So by the definition of tau GH, this is x GH. Now by associative law, this product equals xg times h. First of all, xg is this, and the second thing is this is something, but that something is after all again a group element. So tau h. What is this product? This product is the composition of these two bijections, tau g and tau h, as elements in this group in A of G. Okay. So because we chose x to be any element in G, so these equations tell us that tau GH is tau G times tau H, that is tau GH will be GH psi, and this will be G psi, this will be H psi. So this is a homomorphism. So okay, we have shown that this is a homomorphism, but that's not enough. We want to further know whether this is one-to-one or not. For that, now that we have shown psi is a homomorphism, one-to-oneness will now be equivalent to showing that the kernel of psi, which is here, okay, kernel of psi is a subgroup in the domain group, consists of only the identity element. So let us take any element in the kernel. Now let say what can we take, G, H, I, J, K, anything. Let K belong to the kernel of psi. Recall that this is the notation for the kernel of psi. When we write K suffix a map, which is a group homomorphism, not any other structure homomorphism. Okay, in this book, K psi denotes the kernel of psi. So let K belong to the kernel of psi. Then, by the definition of kernel, the image of K under psi should be the identity element in this what I am saying, identity element in this group. Yes, K is coming from here, it belongs to the kernel, so the image of K should be the identity here. Now the identity in this group is the identity mapping on G, because this group has bijections on G. So this I represents the identity mapping. And this is nothing but, according to the definition of psi, this is tau K. So for any, or instead of writing any x, we can be somewhat more direct. So this E is the identity in our original group. This is equal to EI, because the identity function does not change any element of G. This is the identity function on G. That is now equal to E tau k. By the definition of tau k, this is Ek, and that is equal to k. So see that k is the identity element. So the only element in the kernel of psi is the identity element. So that's why psi is a one-to-one function or an isomorphism. This implies the kernel of psi consists of only the identity elements. Hence, psi is one-to-one. So that means psi maps G into A of G in a one-to-one manner. There is no collapse. No two different elements are getting mapped onto the same element. In a one-to-one manner, it is getting mapped. Its shadow is inside A of G, and that shadow is nothing but the image of G under psi, which we already know is a subgroup of A of G. The image of any group under a homomorphism is always a subgroup. Thus, the image G psi is a subgroup of A of S, where S is the same thing as G, and this is isomorphic to G. So that's how we have identified our abstract group G inside a concrete group A of G. Now we can think of the elements, abstract elements G, as the concrete functions tau G. So this just completes Cayley's theorem. I need some ink. Completes the proof of Cayley's theorem. But now there is a problem. And the problem is this: instead of me saying things verbally, let me just write what the author has written here. The theorem, this theorem that we have proved just now, enables us to exhibit any abstract group as a more concrete object. Yes, that is the aim. And but it has its shortcomings. some people will look down upon this way of presenting things, that is writing some things down on a piece of paper and then sometimes seeing what the things are and then presenting. In a sense it looks bad. It seems like I don't know about these things, that I need to write them down and then see what the things are and then say what they are. But this is not a memory contest, right? And there are so many things, and especially since we have taken the view that we will go through as many things as possible. So I think it's justified that we are unable to remember all the things. So I think this is okay. The main, the aim here is not to show how much I know, but the aim here is to know about these things together. I don't know much. I am just an ordinary student like many of you. Some of you may be experts in some areas, but I am a very ordinary student only, nothing more than that. So it is our struggle to learn about these things and to go through the things rather than showing off how much I know. Okay, that's not the aim here. Okay, so now despite having this achieved, now there are some shortcomings, and one thing is this: if G is a finite group, then if G is a finite group, then we can calculate how many elements this big group has, inside which we have identified G. Recall that this is nothing but the group of all permutations of G. That means the group of all functions which are mapping G onto itself and which are also one-to-one bijective maps. And we already know how many such maps are there. If your G has n elements, then this group has n factorial elements. Now n factorial is larger than n, unless of course n is 1 or 2. As n increases, n factorial also increases, and the gap increases extremely rapidly. When your n is, say, if you write some first few cases, when n is 1, n factorial is 1. When n is 2, n factorial is 2. When this is 3, this is 6. This is 4, this is 24. When n is 5, this is 120. Do you see how rapidly this is increasing? And the gap keeps on increasing and becomes so large that for groups of quite large order, say not that large, but somewhat manageable order, say G is a group of order 100. For such a group, this big group will have 100 factorial elements, and you can imagine how large 100 factorial is. The product of all positive integers starting from 1 all the way up to 100, 1 times 2 times 3 like that. So this group becomes in that case so huge that our tiny G with only 100 elements gets lost inside this extremely huge group. So although you have using Cayley's theorem, you have been able to identify G in a more familiar setting. This is a more familiar avatar of G, but that familiarity has come at the expense of a much more vast space. It is so vast that you are bewildered and you are lost inside this A of G. This is so large, and that is one shortcoming. You may know about A of G quite well because it's a permutation group, but its vastness creates problem. This is lost inside. Okay, you won't be able to find G conveniently inside this. If you lose your focus from this tiny G here with only 100 elements as opposed to the 100 factorial elements in A of G, then that's it. You have lost G. So now the question is, can we make this big group somewhat smaller? And an obvious way to do that is to not take the entire G but something smaller. Okay, so that's what now we want to do. So anyway, let us complete this part. If G is a finite group, then A of G with its order of G factorial elements is much larger than G. This is not how the author has written, but I'm just simply conveying the same thing using slightly different language. Elements in E is much larger than G, and our small g with its order of G elements is somewhat lost in this vastness. Okay, so now we want to use a smaller set S than G in terms of size, so that our A of S is not that large. Okay, it is somewhat more manageable, and we can do that. However, some problems will arise. Then we will see what those problems are. We don't want to take some arbitrary set S which only has in some sense less elements than G. Okay, that will take us very far away from all these nice things we have done here. We want to tweak this situation itself. So what we do is this: let H be a subgroup of G, any subgroup, some subgroup. Let S be the set of all right cosets of H in G, that is, let S be this. Now this S need not itself be a group. In fact, we know that S is a group only if H is normal in G. If H is normal in G, then this is nothing but the quotient group G by H. But that's not necessarily the case here, and we don't even need that actually. The thing is that S now is S set. Okay. So this is the setup. Now if we take this S as our S, what will happen? If we take this S as our S and we carry out a procedure, some arguments that we had in the proof of Cayley's theorem, if we follow a similar path, what do we get? Now define a map. Before defining that, okay, because we have to do the same thing we did, or similar thing we did in Cayley's theorem. We have to write like this: for any G in the group, define, we now need to define again a function like tau of G, tau suffix G. From S to S by, and now our S has the right cosets of H in G. So that means our input will be a right coset, and this G will clash with that G. No? Let us take Hx, and the output will also have to be some right coset of H in G. That we take as Xg. Now unlike tau G, we cannot here immediately say that this Tg is clearly well defined. It will be well defined, but it's not that obvious. So this is one situation where we need to show well definedness. We need to do something. One thing we can immediately see is that for any given input from here, the output at least belongs to S. That much is already obvious. Now, so what else? The next thing we need to show is that two equal inputs give us equal outputs. Let Hx and Hy be two elements in S such that Hx is equal to Hy. The thing that this part is not obvious is because of the fact that a single right coset can have different representations. Here x and y may not be the same group element, but they may give you the same coset. Okay, anyway, so now suppose our inputs are equal. Now we need to show that the outputs are also equal. Then we have already seen these things. When two such cosets are equal, then we have this x y inverse must belong to the subgroup H, or you can also write it like this: x g g inverse y inverse belongs to H, or x g, now g inverse y inverse is yg whole inverse. This belongs to H, and just like you can come from here to here, from here also you can go there. These two things are equivalent. So from here we can go to this hxg equal to hyg, or hxtg equal to hytg. So equal inputs give us equal outputs. Thus now we can say Tg is well defined. Next, same like what we did with tau g. Next thing we need to show is that Tg is 1-to-1 and onto. Next, for any element in the codomain, suppose HA belonging to S, there exists HAG inverse. This is also a right coset of H in G, because AG inverse after all is again a group element from G, capital G. So this belongs to S such that what is the Tg image of this? So this is nothing but HA. So any element has an inverse image under the function Tg. Therefore Tg is onto. Next, one-to-oneness. Let HB and HC belong to S such that HBTG equal to HCTG. Then HBG. So whatever we did here to show that the function is 1-to-1, usually to show that it's whatever we did there to show that the function is well defined, we have to usually do all the we have to do all those things in the opposite order to show that it's 1-to-1. So here we have started by assuming that the outputs are equal. We need to show that the inputs are equal. HCG or BG CG inverse belongs to H. or PGG inverse C inverse belongs to H, or BC inverse belongs to H, or HB is equal to HC, thus TG is 1 to 1. We have thus shown that the function Tg is a bijection and hence it belongs to A of S. Okay, now we can define. In Cayley's theorem we defined psi, which turned out to be an isomorphism. This time we are going to similarly define one such function theta, again from G into A of S, but now our S is not G, it is the set of right cosets of H in G. Why? The definitions are similar. G theta, the image of G under theta is equal to Tg. At this time you can write clearly theta is well defined. Unlike cosets, single group elements, they have only, if nothing else is given, G is just G. There is no 2 or 3 different representations of G. Okay, so this is well defined. Now next, let us show that like tau G, T G is a homomorphism. For that, what are the things we will need? We need G, H and, okay, let G and H be 2 elements in G and H, let's take Hx itself, Hx be an element in S. Then like before, another such calculation, Hx TGH is Hx GH, which because of associativity it is equal to this. TH TG TH and this is Hx Tg composition Th. Keep in mind that Tg and Th are still group elements in A of S. Although S is something else, but A of S, just like before, is still a group, a permutation group. So let us write it at once now. TGH according to our definition of theta is GH theta. This is equal to TGH, and because it has the same effect on Hx as this function, so this is equal to TGTH. TG is G theta, TH is H theta. This implies theta is a homomorphism. So far things have gone in an exactly similar manner. Whatever we had before, we have simply changed S, but all the things we did before, again we are doing similar things. But next, in the order in which the things went back then for tau g and psi, now the next thing is the kernel of theta, like we had the kernel of psi. This, however, will not necessarily consist of only the identity element. Kernel of theta by definition consists of those elements in G which are mapped by theta onto the identity element of what group? A of S. Okay, let's see what it ultimately becomes. So this is equal to identity means what? TG is equal to identity. That means if I apply TG on any right coset of H in G, then I get the right coset itself. Keep in mind that this identity map is the identity mapping on S, and S is the set of all right cosets of H in G. So if you want, you can write I here and then apply the definition of TG, and also because I is identity map on S, you have this. Oh, and okay, I forgot, for all Hx belonging to S, that should be mentioned. So this is how the kernel looks. But although the kernel will not necessarily be just the trivial group, but you can say something about the kernel, and that something is not trivial. The fact is that, see, first things first, because it is the kernel of some homomorphism theta, it will be a normal subgroup of G, since is the kernel of theta, it is a normal subgroup of G. Okay, I hope I am not running out of space again. Let us quickly do this part. So we know that k theta is a normal subgroup of G. What more is true about k theta? For any G belonging to K theta we have Hx G equal to Hx for all Hx belonging to S. In particular, Hg, which is Heg, is equal to He, this is equal to H. E is the identity, and so G belongs to H. So any element in this kernel belongs to H. So this kernel is actually inside H. It's a normal subgroup of G that is inside H, but more is true. Let N be any normal subgroup of G that is contained in H. So N is any normal subgroup of G that is contained in H. K theta is one such normal subgroup that is contained in H, but N is any. For any N belonging to N, we have X N inverse X inverse belongs to N for all X belonging to G, and this we are just simply applying the normality of N in G. Since N is contained in H, that's how we have chosen N. We have X N inverse X inverse belonging to H, or X N inverse whole inverse belonging to H, or, and we have seen already that this means that X Hx is equal to Hxn for all. Now we write for all X belonging to G. That means for all Hx belonging to S. Thus, so now look at the definition, look at the way K theta has ultimately come out to be. So this implies N belongs to K theta, that is capital N is contained in K theta. So not only is K theta a normal subgroup of G contained in H, but it is the largest normal subgroup of G contained in H. Any normal subgroup of G that is contained in H must be inside K theta. So we can say this extra about the kernel, and this entire thing can now be summarized in the form of a result. So although we have not achieved an isomorphism theta, but we have achieved a homomorphism theta whose kernel has some properties. So our aim of identifying G inside A of S and at the same time shrinking S somewhat has not been fulfilled completely, but we have found a homomorphism theta whose kernel has some properties, and these things can now be used, you will see, to say quite a few things about normal subgroups of groups. So the discussion we have gone through gives rise to this. If G is a group, H is a subgroup of G and S is the set of all right cosets of H in G, then there exists a homomorphism theta of G into A of S whose kernel is the largest normal subgroup of G contained in H. Okay, so the previous discussion proves this. Now, before I end this video, let us see why we are doing this. I mean, why suddenly a subgroup and its collection of right cosets? You see, when you take a group, we have already seen these things in the proof of Lagrange's theorem, and you take a subgroup H. Considering the cosets of H, right cosets for example, partitions G into disjoint equivalence classes, and then so that means okay, now instead of the entire G, if one considers the set of such equivalence classes, that means we are considering less. All this, in place of all the points in H, we have a single element H, that is one element of our new set S. Another element here, that is each coset has allowed us to identify the points that it has as a single entity. So that is a collapse. All the points that are inside H that are now considered as a single point, and corresponding local collapses are there, and the entirety of G will come under this process of collapse. And so that means this S has shrunk in size. I mean, you can clearly understand that this is the case when G is a finite group, but in case of infinite groups also there is shrinkage. Although the S may itself be infinite, but in some sense it has got smaller, and that's why we write G pi H as if H is dividing G up into smaller chunks, so that this quotient that remains after division is smaller than the original group. Okay, so if you choose such an S, so you are choosing smaller S, and correspondingly your A of S is somewhat smaller than that original gigantic A of G. We will in the next video we will see what some of the consequences of this thing are. So let me end things here. If you want to say something about these things, you can write in the comment section below. Oh, and today is 2nd, no? 3rd, 4th, 5th. On 5th we will have a field theory upload from topics in algebra. So until then, keep enjoying mathematics. So see you in the next video. This is me, Lucifer, from a mathematical room. Have a nice night.